So, what is profiling in deep learning? Uh, PyTorch and Lightning. So, here we are talking about the second phase of optimization, the second part of the last previous videos here. So, the data pipeline optimization, making data loading faster, and training loop profiling, making the actual model computational faster. So previously, we optimized how data moves from disk to CPU to GPU. Now, the focus is what happens inside the training loop, where the GPU spend time, which operations slow training down. This is called profiling. So, what's profiling? It's monitoring and measuring what happens during model training. Think of it like a doctor checking your heartbeat and blood pressure, a mechanic diagnosing a car engine. The profiler diagnoses slow operations, GPU idle time, memory bottlenecks, expensive layers, inefficient code. The goal is faster training, better GPU utilization, less wasted memory, minimal loss in accuracy. Why profiling matters? Even tiny inefficiencies become huge problems during training. Example, suppose one batch wastes 20 milliseconds and you train on 1 billion batches. So therefore, that tiny waste becomes 20 milliseconds multiplied by 1 billion batches. That is 20,000 seconds. That is 330 minutes, more than 5 hours wasted. So optimization matters enormously at scale. The training loop, um, so here, training loop contains forward pass, backward pass, and wait updates. So let's break this down. So the forward pass input flows through the network from the input to convolution to ReLU, the activation function, and it's linear, the flat end. The model predicts outputs. And backward pass, PyTorch computes gradients using backpropagation. This is usually the most expensive part. Why? Because gradients must be computed for every every layer, every activation. Convolution backward passes are especially expensive. And the weight update. Optimizer updates parameters like the new weights or the new parameters is equivalent to the old parameters subtracted by the gradients multiplied by the learning rate. So, what question does the profiler answer? So, the PyTorch profiler helps answer which operations consume the most time. Example, convolution, matrix multiplication, and backward pass. And is the GPU fully utilized? Sometimes the GPU waits for CPU processing, data transfer, synchronization. This creates GPU idle time. Are there memory bottlenecks? Maybe tensors are too large, activations consume too much memory, memory fragments occurs, and which code lines are slow. The profiler can trace operations back to code sections. And why we use Lightning? So, because raw PyTorch profiling requires lots of boilerplate code or repetitive code. Lightning simplifies training loops, profiling integration, logging, device handling. It separates model logic from engineering details, so we could focus on the neural network instead of repetitive infrastructure code. And core profiler configuration. The lesson configures a PyTorch profiler. Let's analyze every part carefully. So the output directory is, we initialize it in directory path, the profiler logs, and the file name. Let's say the file name is profile. This tells Lightning what to say profiling results, what to name the report. The profiler generates trace files you can inspect later. And next is understanding the profiling scheduler. This is the most important concept. The schedule controls when profiling occurs. Like example, weight is equivalent to So profiler does nothing for the first two steps. Why? Early training contains unstable setup overhead, CUDA initialization, memory allocation, kernel complication for the first two steps. Those are not representative of real training speed, so we ignore them. And next is warm up is equivalent to 2. The profiler starts monitoring but discards the measurements. Why? The GPU is still stabilizing. This avoids skewed benchmark results. Things of warming up, like warming up before exercise, reviving a car engine before measuring speed. Next is active is equivalent to 10. Now the profiler records real measurements. These 10 steps becomes the actual profiling data. And next is repeat is initialized or equivalent to 1. The entire cycle runs once. So the full cycle is the pace wait is 2 steps, the warm up is 2 steps, and the active is 10 steps. So overall total is 14. So why max steps equivalent to 14? So this matches the profiling schedule exactly because there's a 2 wait, 2 warm up, and 10 actives. That's equivalent to 14. If training ended earlier, the profiler would not complete its cycle. Next is profile memory is equivalent to true. This tracks GPU or CPU memory usage. Extremely useful for diagnosing the out of memory errors or OOM, and memory leaks, oversized activations, excessive tensor allocations. Next is accelerator equivalent to auto. Lighting automatically chooses GPU if available, otherwise we'll use CPU, and it's very convenient. Next is device equivalent to 1. Train on one GPU device only. Simplifies profiling, and multi-GPU profiling becomes more complicated. Why disable logger and model summary? Like logger is equal to false, enable model summary is equal to false. This keeps the output clean. Otherwise, training logs, progress bars, model summaries would clutter the profile output. Next is running the profiler. So the code is trainer.fit, and its argument is model and DM loader. This single line trains the model, runs the profiler, collects metrics, and stores traces. Lighting orchestrates everything automatically. And what does the profiler output show? The profiler output tables, like we have the column of operation and the total time. Like for example, we have the profiler step, and its value in the total time is 500 milliseconds, and convolutional backward is 300 milliseconds for example, and convolutional is 200 milliseconds for example. Next is understanding the profiler step. The top operation was profiler step. This represents the total duration of one training iteration, including the forward pass, backward pass, optimizer step, synchronization. So it's the overall batch processing time. And why convolution backward is expensive? So because convolution backward pass and convolution operations were very expensive. This is normal. Convolutions are computationally heavy because they involve massive tensor operations. Backward pass is even heavier because gradients must be computed. Here's the key insight in the model complexity matters. The original model was, let's say we have the layer and channels. Let's say the convolutional 1 is 256, convolutional 2 is 512, and convolutional 3 is 1024, and the linear is 2048 channels. This is huge for the Cypher 10. Remember, Cypher 10 images are only 32 by 32. That's very small. So the model was overkill. Next is efficient model. The optimized model became the layer 1 from the 256 convolutional. It's now becomes 32. It matches to the data set we have, the Cypher 10. Then the convolutional 2 is 64, convolutional 3 is 128, and the linear is 512. That's much smaller. And why smaller models train faster? Because convolutional cost grows with channel count. Very roughly, we have the cost and the channel out. So reducing channels massively reduces computation, memory, and gradient cost. So the result of simplification, training loop time nearly halved, accuracy only dropped slightly. This is huge optimization win. So the meaning is much faster training, minimal performance sacrifice. This is one of the most important lessons in deep learning engineering. Bigger models are not always better. And the main workflow we should understand is optimization workload. Yes, step 1 is train normally, establish baseline performance. Step 2 is profile, use the profiler to identify slow operations, GPU stalls, memory hotspots. And step 3 is diagnose bottlenecks. Example, convolution is too expensive, data loading is too slow, and GPU waiting for CPU. Next, step 4 is to optimize. Possible optimizations is simplify architectures, reduce channels, reduce layers, makes precision, faster data loaders, and gradient checkpointing. Next is profile, measure improvement objectively, never optimize blindly. And the most important concept is profiling teaches performance intuition. Eventually, you recognize expensive operations, wasteful architectures, memory inefficiencies without guessing. That intuition is what separates someone who can train models from someone who can engineer efficient systems. So, to summarize, fast data loading alone is not enough. The training loop itself can bottleneck performance. PyTorch Profiler helps identify inefficiencies, and Lighting simplifies profiling integration, and profiling schedules avoid misleading measurements, and convolution backward passes are often expensive, and simpler architectures can dramatically improve speed. Optimization is always a balance between speed, memory, accuracy, and that's